Granite.
Granite/ggranite/ is a common type of felsic intrusive igneous rock which is granular and phaneritic in texture. The word granite comes from the Latin granum, a grain, in reference to the coarse-grained structure of such a holocrystalline rock. The term granite also applies to a group of intrusive igneous rocks with similar textures and slight variations on composition and origin. These rocks mainly consist of feldspar, quartz, mica, and amphibole minerals. These form interlocking somewhat equigranular matrix of feldspar and quartz with scattered darker biotite mica and amphibole peppering the lighter color minerals. Occasionally some individual crystals are larger than the groundmass, in which case the texture is known as porphyritic. A granitic rock with a porphyritic texture is known as a granite porphyry. Granites can be predominantly white, pink, or gray in color, depending on their mineralogy. By definition, granite is an igneous rock with at least 20% quartz and up to 65% alkali feldspar by volume. Granite differs from granodiorite in that at least 35% of the feldspar in granite is alkali feldspar as opposed to plagioclase. It is the potassium feldspar that gives many granites a distinctive pink color. The extrusive igneous rock equivalent of granite is rhyolite. Granite is nearly always massive, lacking any internal structures, hard and tough, and therefore it has gained widespread use throughout humanity, and more recently as a construction stone. The average density of granite is between 2.65 and 2.75 grams per centimeter 3. Its compressive strength usually lies above 200 MPa, and its viscosity near STP is 3-6-10-19 pascals by second. Melting temperature is 1215 to 1260 DEGC. Granite has poor primary permeability but strong secondary permeability. Granitoid is a general, descriptive field term for lighter-colored, coarse-grained igneous rocks. Petrographic examination is required for identification of specific types of granitoids. The term granitic means granite-like and is applied to granite and rocks of similar composition or texture.
Mineralogy.
Granite is classified according to the QAPF diagram for coarse-grained plutonic rocks and is named according to the percentage of quartz, alkali feldspar, orthoclase, sanidine, or microcline, and plagioclase feldspar on the AQP half of the diagram. True granite according to modern petrologic convention contains both plagioclase and alkali feldspars. When a granitoid is devoid or nearly devoid of plagioclase, the rock is referred to as alkali feldspar granite. When a granitoid contains less than 10% orthoclase, it is called ternolite. Pyroxene and amphibole are common in ternolite. A granite containing both muscovite and biotite micas is called a binary or 2-mica granite. 2-mica granites are typically high in potassium and low in plagioclase, and are usually S-type granites or A-type granites.
Chemical composition.
A worldwide average of the chemical composition of granite, by weight %, based on 2485 analyses.
Occurrence.
Outcrops of granite tend to form tors and rounded massifs. Granites sometimes occur in circular depressions surrounded by a range of hills, formed by the metamorphic aureole or horn fells. Granite is usually found in the continental plates of the Earth's crust. Granite is currently known only on Earth, where it forms a major part of continental crust. Granite often occurs as relatively small, less than 100 km 2 stock masses, stocks, and in batholiths that are often associated with rhyogenic mountain ranges. Small dikes of granitic composition called eplites are often associated with the margins of granitic intrusions. In some locations, very coarse-grained pegmatite masses occur with granite. Granite has been intruded into the crust of the Earth during all geologic periods, although much of it is of Precambrian age. Granitic rock is widely distributed throughout the continental crust and is the most abundant basement rock that underlies the relatively thin sedimentary veneer of the continents.
Origin.
Granite is of felsic composition and is more common in recent geologic time in contrast to Earth's ultramafic ancient igneous history. Felsic rocks are less dense than mafic and ultramafic rocks, and thus they tend to escape subduction, whereas basaltic or gabbroic rocks tend to sink into the mantle beneath granitic rocks of the continental cratons. Therefore, granitic rocks form the basement of all land continents.
Geochemical origins.
Granitoids are a ubiquitous component of the crust. They have crystallized from magmas that have compositions at or near a eutectic point, or a temperature minimum on a catectic curve. Magmas will evolve to the eutectic because of igneous differentiation, or because they represent low degrees of partial melting. Fractional crystallization serves to reduce a melted iron, magnesium, titanium, calcium and sodium, and enrich the melted potassium and silicon. Alkali feldspar, rich in potassium, and quartz, CO2, are two of the defining constituents of granite. This process operates regardless of the origin of the parental magma to the granite, and regardless of its chemistry. However, the composition and origin of the magma which differentiates into granite, leaves certain geochemical and mineral evidence as to what the granite's parental rock was. The final mineralogy, texture and chemical composition of a granite is often distinctive as to its origin. For instance, a granite which is formed from melted sediments may have more alkali feldspar, whereas a granite derived from melted basalt may be richer in plagioclase feldspar. It is on this basis that the modern alphabet classification schemes are based. Granite has a slow cooling process which forms larger crystals.
Chappell and White classification system.
The letter-based Chappell and White classification system was proposed initially to divide granites into I-type granite, or igneous protolith, granite and S-type or sedimentary protolith granite. Both of these types of granite are formed by melting of high-grade metamorphic rocks, either other granite or intrusive mafic rocks, or buried sediment, respectively. M-type or mantle-derived granite was proposed later, to cover those granites which were clearly sourced from crystallized mafic magmas, generally sourced from the mantle. These are rare, because it is difficult to turn basalt into granite via fractional crystallization. A-type or anerogenic granites are formed above volcanic hotspot activity and have peculiar mineralogy and geochemistry. These granites are formed by melting of the lower crust under conditions that are usually extremely dry. The rhyolites of the Yellowstone caldera are examples of volcanic equivalents of A-type granite. H-type or hybrid granites are formed following a mixing of two granitic magmas from different sources, for example M-type and S-type.
Granitization.
An old, and largely discounted theory, granitization states that granite is formed in place by extreme tasematism by fluids bringing in elements, for example potassium, and removing others, for example calcium, to transform the metamorphic rock into a granite. This was supposed to occur across a migrating front. The production of granite by metamorphic heat is difficult, but is observed to occur in certain amphibolite and granule terrains. In situ granitization or melting by metamorphism is difficult to recognize except where leucosome and melanosome textures are present in migmatites. Once a metamorphic rock is melted, it is no longer a metamorphic rock and is a magma, so these rocks are seen as a transitional between the two, but are not technically granite as they do not actually intrude into other rocks. In all cases, melting of solid rock requires high temperature, and also water or other volatiles which act as a catalyst by lowering the solidus temperature of the rock.
Ascent and emplacement.
The ascent and emplacement of large volumes of granite within the upper continental crust is a source of much debate amongst geologists. There is a lack of field evidence for any proposed mechanisms, so hypotheses are predominantly based upon experimental data. There are two major hypotheses for the ascent of magma through the crust. ๊ɡrænɨt, fracture propagation. Of these two mechanisms, ๊ɡrænɨt was favored for many years in the absence of a reasonable alternative. The basic idea is that magma will rise through the crust as a single mass through buoyancy. As it rises, it heats the wall rocks, causing them to behave as a power law fluid and thus flow around the pluton, allowing it to pass rapidly and without major heat loss. This is entirely feasible in the warm, ductile lower crust where rocks are easily deformed, but runs into problems in the upper crust which is far colder and more brittle. Rocks there do not deform so easily. For magma to rise as a pluton it would expend far too much energy in heating wall rocks, thus cooling and solidifying before reaching higher levels within the crust. Fracture propagation is the mechanism preferred by many geologists as it largely eliminates the major problems of moving a huge mass of magma through cold brittle crust. Magma rises instead in small channels along self-propagating dikes which form along new or pre-existing fracture or fault systems and networks of active shear zones. As these narrow conduits open, the first magma to enter solidifies and provides a form of insulation for later magma. Granitic magma must make room for itself or be intruded into other rocks in order to form an intrusion, and several mechanisms have been proposed to explain how large batholiths have been emplaced. Stopping, where the granite cracks the wall rocks and pushes upwards as it removes blocks of the overlying crust. Assimilation, where the granite melts its way up into the crust and removes overlying material in this way. Inflation, where the granite body inflates under pressure and is injected into position. Most geologists today accept that a combination of these phenomena can be used to explain granite intrusions, and that not all granites can be explained entirely by one or another mechanism.
Weathering.
When granite and other similar rocks weather, two primary effects are seen. On a large scale, exfoliation joints are produced as the granite weathers. On a small scale, grass is formed as the minerals within the granite break apart. Climatic variations also influence granitic erosion rate. For about 2,000 years, the relief engravings on Cleopatra's Needle obelisk had survived the arid conditions of its origin prior to its transfer to London. Within 200 years, the red granite has drastically deteriorated in its new moist climate.
Natural radiation.
Granite is a natural source of radiation, like most natural stones. However, some granites have been reported to have higher radioactivity, thereby raising some concerns about their safety. Potassium-40 is a radioactive isotope of weak emission, and a constituent of alkali feldspar, which in turn is a common component of granitic rocks, more abundant in alkali feldspar granite and syenites. Naturally, a Geiger counter should register this low effect. Some granites contain around 10 to 20 parts per million, ppm, of uranium. By contrast, more mafic rocks such as tonalite, gabbro or diorite have 1 to 5 ppm uranium, and limestones and sedimentary rocks usually have equally low amounts. Many large granite plutons are the sources for paleocanal-hosted or roll-front uranium ore deposits, where the uranium washes into the sediments from the granite uplands and associated, often highly radioactive, pegmatites. Cellars and basements sunk into soils over granite can become a trap for radon gas, which is formed by the decay of uranium. Radon gas poses significant health concerns, and is the number 2 cause of lung cancer in the U.S. behind smoking. Thorium occurs in all granites as well. Conway granite has been noted for its relatively high thorium concentration of 56, ±6, ppm. There is some concern that materials sold as granite countertops or as building material may be hazardous to health. Dan Steck of St. John's University has stated that approximately 5% of all granite will be of concern, with the caveat that only a tiny percentage of the tens of thousands of granite slab types have been tested. Various resources from National Geological Survey organizations are accessible online to assist in assessing the risk factors in granite country and design rules relating, in particular, to preventing accumulation of radon gas in enclosed basements and dwellings. A study of granite countertops was done, initiated and paid for by the Marble Institute of America, in November 2008 by National Health and Engineering Incorporated of USA, and found that all of the 39 full-size granite slabs that were measured for the study showed radiation levels well below the European Union's safety standards, Section 4.1.1.1 of the National Health and Engineering Study, and radon emission levels well below the average outdoor radon concentrations in the U.S.
Uses. Antiquity.
The Red Pyramid of Egypt, c. 26th century BC, named for the light crimson hue of its exposed granite surfaces, is the third largest of Egyptian pyramids. Menkau's pyramid, likely dating to the same era, was constructed of limestone and granite blocks. The Great Pyramid of Giza, c. 2580 BC, contains a huge granite sarcophagus fashioned of red-as-one granite. The mostly ruined Black Pyramid dating from the reign of Amenemhat III once had a polished granite pyramidion or capstone, now on display in the main hall of the Egyptian Museum in Cairo, see Dahshur. Other uses in ancient Egypt include columns, door lintels, cells, jambs, and wall and floor veneer. How the Egyptians worked the solid granite is still a matter of debate. Dr. Patrick Hunt has postulated that the Egyptians used emery shown to have higher hardness on the Mohs scale. Raja Chola I of the Chola dynasty in South India built the world's first temple entirely of granite in the 11th century AD in Tanjore, India. The Brihadeeswara temple dedicated to Lord Shiva was built in 1010. The massive gopuram, ornate, upper section of shrine, is believed to have a mass of around 81 tons. It was the tallest temple in South India. Many large Hindu temples in southern India, built by the Chola, Emperor Raja Chola I, were made of granite. There is a large amount of granite in these structures. They are comparable to the Great Pyramid of Giza.
Modern sculpture and memorials.
In some areas granite is used for gravestones and memorials. Granite is a hard stone and requires skill to carve by hand. Until the early 18th century, in the Western world, granite could only be carved by hand tools with generally poor results. A key breakthrough was the invention of steam-powered cutting and dressing tools by Alexander MacDonald of Aberdeen, inspired by seeing ancient Egyptian granite carvings. In 1832 the first polished tombstone of Aberdeen granite to be erected in an English cemetery was installed at Kensal Green Cemetery. It caused a sensation in the London monumental trade and for some years all polished granite ordered came from MacDonald's. Working with the sculptor William Leslie, and later Sidney Field, granite memorials became a major status symbol in Victorian Britain. The royal sarcophagus at Frogmore was probably the pinnacle of its work, and at 30 tons one of the largest. It was not until the 1880s that rival machinery and works could compete with the MacDonald works. Modern methods of carving include using computer-controlled rotary bits and sandblasting over a rubber stencil. Leaving the letters, numbers and emblems exposed on the stone, the blaster can create virtually any kind of artwork or epitaph.
Buildings.
Granite has been extensively used as a dimension stone and as flooring tiles in public and commercial buildings and monuments. Aberdeen in Scotland, which is constructed principally from local granite, is known as the Granite City. Because of its abundance, granite was commonly used to build foundations for homes in New England. The Granite Railway, America's first railroad, was built to haul granite from the quarries in Quincy, Massachusetts, to the Neponset River in the 1820s. With increasing amounts of acid rain in parts of the world, granite has begun to supplant marble as a monument material, since it is much more durable. Polished granite is also a popular choice for kitchen countertops due to its high durability and aesthetic qualities. In building and for countertops, the term granite is often applied to all igneous rocks with large crystals, and not specifically to those with a granitic composition.
Engineering.
Engineers have traditionally used polished granite surface plates to establish a plane of reference, since they are relatively impervious and inflexible. Sandblasted concrete with a heavy aggregate content has an appearance similar to rough granite, and is often used as a substitute when use of real granite is impractical. A most unusual use of granite was in the construction of the rails for the Hayter Granite Tramway, Devon, England, in 1820. Granite block is usually processed into slabs and after can be cut and shaped by a cutting center. Granite tables are used extensively as a base for optical instruments due to granite's rigidity, high dimensional stability and excellent vibration characteristics.
Other uses.
Curling stones are traditionally fashioned of Ailsa-Craig granite. The first stones were made in the 1750s, the original source being Ailsa-Craig in Scotland. Because of the particular rarity of the granite, the best stones can cost as much as $1,500. Between 60 to 70% of the stones used today are made from Ailsa-Craig granite, although the island is now a wildlife reserve and is no longer used for quarrying.
Rock climbing.
Granite is one of the rocks most prized by climbers, for its steepness, soundness, crack systems, and friction. Well-known venues for granite climbing include Yosemite, the Bugaboos, the Mont Blanc Massif, and peaks such as the Aiguille du Drap, the mountains of Morne, the Adamolo-Presanella Alps, the Aiguille du Midi and the Grand Jorasses, the Bregaglia, Corsica, parts of the Caraco Ram, especially the Trango Towers, the Fitzroy Massif, Patagonia, Baffin Island, Ogawa, the Cornish coast, the Cairn-Worms, Sugarloaf Mountain in Rio de Janeiro, Brazil, and the Storamos Chief, British Columbia, Canada. Granite rock climbing is so popular that many of the artificial rock climbing walls found in gyms and theme parks are made to look and feel like granite.